Lesson number 16, daily summary. In this lesson, we simplify expressions that contain radicals. This lesson is a bit unusual in that we have 2 demos and 2 activities. We know that the square root of 49 is 7, since 7 times 7 is 49, and that's 2 copies because it was a square root. Similarly, the cube root of 64 is 4, since 4 times 4 times 4, 3 copies of that number, equals 64. Important vocabulary today includes the terms radicand, index, and radical sign. Each is illustrated here, so we'll just kind of circle some stuff. The radicand is the thing inside, and the index is this tiny little number right up here. And then finally, the radical sign is just that symbol. Yeah, so that symbol right there is the radical sign. Also right here. Let's look at some other radicals. The first page of this packet will be helpful for these. So the first one is the cube root of 125. You might happen to know what it is, but even if you already know what it is, take a look at that first page of the packet, which you should have ripped off already. And on that first page, you see that big chart of numbers. This is a cube root, so look in the column that says perfect cubes. You'll find the numbers 1 and 8 and 27 and 64. We are looking for the number 125 in that list. It's the very next one after 64. And then you read all the way to the left. That first column tells you that the answer is 5. Cube root of 125 is 5. Similarly, find the 4th root of 81. Pause the video and come back when you got it from that chart. So in this case, we look in the 4th powers column. We find the number 81. Read all the way to the left, and we see the answer is 3. And then finally, the square root of 289. Pause the video and come back when you found it on your chart. So in this case, we're looking at the perfect squares and look to the left and we see 17 is the answer. Number 4, find the value of each of the following radical expressions. Square root of 9 times 4, for sure, is square root of 36, which is definitely 6. Let's do this similar but different calculation in part B. Square root of 9 times square root of 4, that is 3 times 2, which is also 6. And it is no coincidence that these two answers were the same. It turns out that when you have multiplication inside of a radical, you could do the multiplication first and then take the square root like we did here, or you could take the square roots first and then multiply them last, and you'll get exactly the same answer either way. And it's not just true for square roots, it's also true for any root. So here's the product rule for radicals. Multiplication inside of an nth root, doesn't matter what the root is. You could do the roots separately, both of them get the same n, and then multiply your answers at the end. Division is similarly nice. If you have a fraction inside of a radical, you could do 2 separate radicals and then divide them at the end, and you will get the same answer. Number 6, let's find the value of each of the following radical expressions. Square root of 9 plus 4 compared to square root of 9 plus square root of 4. Everything works so nicely up above with multiplication and division. Maybe it'll work nicely with addition as well. This is square root of 13, which is, 3 point something. And on part B, this is really 3 plus 2, which is 5, which is definitely not the square root of 13. So it is not true that the square root of 9 plus 4 is equal to the square root of 9 plus square root of 4. We just saw it. We get 2 totally different answers. So we put a big old X. It simply does not work. You cannot separate radicals over addition or subtraction. Number 7, radicals of the form square root of x plus y and square root of x minus y cannot be simplified. Do not be tempted to kind of distribute that square root through. In particular, square root of a squared plus b squared is not equal to a plus b. Put a few more angry lines through that equal sign. Number 8 says, let's simplify the 4th root of 48. So we know that multiplication behaves well inside of a radical, so we factor 48. And there are a number of ways to do this. One is useful, but the rest are not. So let's take a look here. 4th root of 48, we're trying to simplify it. I guess we probably first should look on our perfect 4th powers column and see if 48 is in there. It isn't, but that's the first attempt. So then we see if we can factor 48. Well, sure, we can factor 48 in any number of ways. 48, for example, is equal to 24 times 2. And then using our brand new product rule, we can split this up into 2 radicals. 4th root of 24 times the 4th root of 2. So go take a look at your perfect fourth powers column again. Is 24 in that list? No. Is 2 in that list? No. So even though all of these equal signs are true, we haven't gotten any place useful. But let's take a look at this second method. Instead of factoring 48 as 24 times 2, let's factor 48 as 16 times 3. And then again, use our brand new product rule, 4th root of 16 times the 4th root of 3. Now the 4th root of 3 is nothing nice, it's irrational, but the 4th root of 16 is a very nice number. It's on your sheet, your chart there if you don't happen to know it, but the 4th root of 16 is 2, plain 2, not 4th root of 2, just plain 2. And then you copy the 4th root of 3. And so we say that we have simplified this radical here. The 4th root of 48 is 2 times the 4th root of 3, and that is simplified. In the same way that 6 over 9, you would never leave that as a final answer. You would always simplify that answer, and you get to 2/3. It is now our obligation to simplify radicals in exactly this way. And the goal is to pull out the biggest thing that you can, the biggest perfect fourth power in this case, which was 16. I will point out that you could, for example, do this. It's not going to be helpful, but you could do 4th root of 48. You can find the biggest fourth power that's less than 48. And again, that's 16. So you could write this. You could say, okay, 16 plus, and then what do you have to add to still get 48? All right, so I guess it's 32. But there's no place to go from here. Like it's tempting to do, you know, like this 4th root of 16 plus the 4th root of 32, but we can't. It's simply not true. We get some more angry red lines going through that equation. It just doesn't work. And so you shouldn't bother trying to take that 48 and write it as the sum of two things because there's nowhere to go from there. It's always about looking for a factor of 48. Okay, let's take a look at number 9. Here's how we simplify square root of 12 minus 2 square root of 75. So we look at square root of 12. There are a few different ways to factor square root of 12. Could do 6 times 2 or 3 times 4. Only one of them is useful, so let's not factor 12 willy-nilly. Let's think about the perfect squares. This is a square root, that's why I'm thinking about perfect squares. So looking at our perfect squares list, look at that column. You see 1, 4, 9, 16. You're looking for a perfect square that goes into 12. What is it in that list? It's 4. So that means that you rewrite 12 as 4 times something, in this case 4 times 3. Same game with the 75. Look for a number in the perfect squares list that goes into 75. Don't just factor 75 willy-nilly. For example, 75 is 5 times 15. It's true, it's not helpful. Find a perfect square that goes into 75. Hopefully we see it is 25, and in particular 75 is 25 times 3. Everything else in here has been copied. All we've done is factor 12 in a particular way and factor 75 in a particular way. Then we start splitting up because of our product rule. We can split this into 2 radicals here. We can split this into 2 radicals here. Notice that the 2 sitting in the front is still sitting in the front. I'm highlighting the fact that it's multiplication right there, 2 times the radical. Okay, and then good things start to happen. Square root of 4 is just plain 2, so there is a just plain 2. Nothing to do with the square root of 3 besides copy it down. Square root of 25 is 5 right there. And this is the most important point, is that multiplication is still sitting here. Lots of arrows over there. It is 2 times 5. It is not 2 plus 5. All too often I'll have students that just they invent a plus sign where there wasn't one. This is not 2 plus root 75, so it is not 2 plus 5 root 3. There's an invisible multiplication dot right there. Let's make it visible when we pull that 5 outside. Okay, then we actually do the 2 times 5 and get 10. So 2 radical 3 minus 10 radical 3. And we can actually combine those two things. Those are called like radicals. If I gave you, for example, 2x minus 10x, you would say, no problem, that is negative 8x. And this is the same format. It's just instead of x, we have radical 3. And so we combine our like radicals. And instead of getting negative 8x, we get negative 8 radical 3. It's really tempting to maybe do something funky with the radical 3's. It doesn't become radical 6 or radical 9, or if you subtract the 3's, radical 0. These x's, oh, I'm just totally lost an x here. Let's try that again. 2x minus 10x is what I meant to write there. And so the x doesn't change at all, right? Like you didn't make it x squared here or 2x there. You were just counting x's. You had 2 x's, you lost 10 x's, so you're left with negative 8 x's. X does not change, it's just a placeholder. Note that we can only add and subtract radicals if they are like radicals. Radicals are like if they have the same radicand and the same index. That is to say, the same thing on the inside and the same little tiny number in the top left of the radical. So let's take a look at these two here. So those two radicals have something that's the same, but something that's different. So what's the same is the fact that they're both square roots. It's not like one is a cube root and one is a fourth root. They're both exactly the same kind of root. That is to say, they're both the same index. But what's different about them is the radicand. There's a 3 and a 5, and this is like 2 apples minus 10 oranges. You can't say anything. You can't combine those two in any way. Okay, let's take a look at these two here. Again, something is the same, but something is different. So what's the same is the radicand. They're both 3 on the inside, but what's different are the indices. One of them is a square root, the other is a 7th root. You cannot combine those in any way. Okay, so that's demo number 1. Go ahead and do activity number 1, and then come back and check out the video for demo number 2, which will be a separate video in this playlist.